Greetings and welcome to the final exam review for Chemistry 221. This final exam review is going to be similar to the other exam reviews we've had, where I will give you a series of questions which are definitely worthy of the final exam, and I'll give you a few minutes to work on the questions in the video, and then I would recommend pausing the video so you can have as much time as you want. And then I will talk about the answer to the video afterwards. We'll go over in detail and stuff like how it works. So again, definitely on this video, I encourage you to pause the video when I say pause the video, and then you can work on the problem and then unpause the video to listen and see how you did and stuff like that. This final exam review will be only over Chapter 6. The actual final exam will have questions from Chapters 1 through Chapter 6, all the chapters we've looked at in Chem 221. But because the Chapter 6 is the newest stuff, I wanted to focus on that material more than the previous material. Cool. Assuming that this is an online class of Chem 221 that you're taking, just as a quick review, chapters 1 through 6 are what's going to be on the actual lecture final. So even though this review is only chapter 6 material, there will be stuff from chapters 1 through chapters 5. So naming, significant figures, thermochemistry, etc., etc. And again, if this is an online class, then this final exam will be due Friday at 9 a.m. via email. I should have your grades posted by Sunday at noon. That's usually what I aim for final exams. A little flexibility definitely appreciated. I do not return final exams to students, but you will be able to check your grades online and through the My MHCC portal pretty soon. So I encourage you to rock this. I definitely wish you best of luck with your studying, and if there are no further questions, let's start the review. This first question says, how many emission lines are possible considering only the first 5 quantum levels of hydrogen shown below? This is basically a question about Bohr's model of the atom, and absorbance lines are when the transitions start at a lower N and they go to a higher N, i.e. an endothermic process. But emission lines, which is what we're looking at right now, emission lines are for starting at a higher N and going to a lower N. So see if you can use this information and the diagram that might be helpful there on the right and figure out how many possible emission lines there can be for the first 5 levels of hydrogen. So pause your video now. Okay, at this point, I'm going to assume that you have worked on this question and you want to see how you did. So without further ado, let's get into the answer. So as I said earlier, emission lines are electron level transitions where you start at a higher N and you go to a lower N. Now, all electrons start off at N equals 1. That's the closest place to the nucleus. And an absorbance line means you go from a lower N to a higher N. Absorbance lines are endothermic, all right? And that's why the arrows are getting bigger, lower to bigger. But these are emission lines. So as an example, let's say you had an electron starting up here at the N equals 5 level. Well, that electron after a while would maybe relax back down to the N equals 1 level. That would be exothermic. It went from a higher energy to a lower energy. That would be the releasing of energy. So the 5 to 1 transition is an emission line. But you could also have a 5 to 2. It doesn't have to go to 1 necessarily, right? You could have a 5 to 3 and a 5 to 4. So those are 4 emission lines right there. But you don't have to start at N equals 5. You could start at N equals 4. And N equals 4 to N equals 1 would be 1 transition. You could also have a 4 to 2 or a 4 to 3. So those are 4 from N equals 5, 3 from N equals 2. You could also have it start at N equals 3, N equals 3 to 1, or N equals 3 to 2. That's 2 more. And then finally, you could also have a 2 to 1 transition. So there's 4 in this initial group, 3 here, 2 here, 1 here, 4 plus 3 plus 2 plus 1, I believe that's 10. Now another way, instead of writing arrows, which is what I did in the diagram there, you could write 5 to 4, 5 to 3, 5 to 2, etc., etc. Those are alternative ways to represent the number of emission lines. But in the end, you should have 10 emission lines from the first 5 levels for hydrogen. You would also, of course, have 10 absorbance lines, but those arrows would be going up. They would be endothermic instead of the exothermic emission lines that we're looking at in this problem. Photons of the highest frequency will be emitted in a transition from level n equals something to n equals something. Now, like on the last question, when we talked about emission lines, we talked about how basically the length of the line is related to energy. And this question asks about frequency, which has a relationship to energy. See if you can use this information to figure out which of those possible answers is the correct one. So at this time, I would encourage you to pause the video, work on your question, and when you're ready, you can unpause it. Pause the video now. Okay, I'm going to assume you've worked on this question and you're ready to look at the answer, which is fantastic. All right, highest frequency. All right, we have to go back to the idea of Planck's constant, where E equals h nu and E equals hc over lambda. And highest frequency, which is the new part right here, means highest energy. So if we can find which of those gaps would be the highest energy, we would then that would then correspond to the highest frequency. Frequency and energy are proportional to each other. Now, this y-axis right here, pretty sloppy arrow, is an energy axis. So the bigger the gap we're going to get, the bigger the transition, the bigger the energy, which means the biggest frequency. And as you can probably imagine, if you have an n equals 5 to n equals 1, that's going to be the biggest energy gap you can get. The levels get closer as you get higher in n, but the 5 to 1 should be the biggest transition, and that's going to be your answer, answer E. So the biggest arrow is the biggest gap between the levels, and because it's an energy axis, that means the 5 to 1 would have the highest energy transition. And then, because energy and frequency are proportional to each other, highest energy would mean highest frequency. So 5 to 1, highest frequency, because it's highest energy, etc., etc. That would also correspond to the smallest wavelength, but we're not really talking about that in this problem. The emission line having the longest wavelength corresponds to a transition from blank to blank. Now, this is kind of the opposite of the problem we just did when it was asking about highest frequency. Now we want the biggest wavelength. So see if you can use your knowledge of the material we've already talked about, plus your current knowledge, to figure out the answer to this question. I encourage you to pause the video, work on it. Pause your video now. Okay, I'm going to assume that you've worked on this question and you'd like to check it out, so let's do it. So earlier in the last example, E equals h nu. We used that to see that the highest frequency came from the highest energy, but we also had the equation E equals hc over lambda. So energy and wavelength are inversely proportional to each other. So for example, then big energy, like on the last one, meant smallest wavelength. But in this question, we want longest wavelength, biggest wavelength. And because they're opposite, the biggest wavelength would come from the smallest energy. So on the gaps over there on the right side with the levels, we want the smallest transition, not the biggest, which was 5 to 1. We want the smallest. And you can probably see that going 5 to 4 is going to be the smallest gap, smallest energy transition. And smallest energy means longest wavelength. So 5 to 4 here is going to be the best answer. Largest wavelength, smallest energy, good to go. Excited hydrogen atoms emit visible light when electrons fall from higher levels to n equals 2. This is part of the hydrogen spectrum lab we did and stuff like that, by the way. These lines are called the Balmer series of lines. Green light comes from n equals 4 to n equals 2. So would you expect the light from n equals 3 to n equals 2 be red or blue? Ultramagnetic is not really a real answer here. Ultramagnetic was part of a band from the 80s, Ultramagnetic MCs, that I was into at the time, so my apologies for the cheesy answer. The answer will be red or blue. Anyway, think about this question. I encourage you to pause the video, think about it, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm assuming that you've worked on the problem and you want to check out your answer, which is fantastic. All the Balmer lines end at n equals 2. N equals 1 is quite a ways below that. All right, and n equals 1 transitions are associated with visible light. But anyway, what's going on here? As the n values get bigger, the gaps get a little bit smaller, but they are bigger. So here's n equals 3, n equals 4, n equals 5, etc., etc. And it says that the 4 to 2 transition is green, okay? That's a green light. So notice that that is the gap from 4 to 2. Now, this question is about the 3 to 2 gap. And you can see that 3 to 2 is a smaller energy gap than the 4 to 2. So for this question, the 3 to 2 gap will be lower in energy than the 4 to 2. And green is kind of halfway in the middle of the visible spectrum. Red would be lower energy, blue would be higher energy. So because 3 to 2 would be lower energy, we're going to expect that one to be red. Lower energy is usually red, higher energy is usually blue, and green is in the middle. So this is just kind of a cool way to use your knowledge of visible light and also what these transition means to see which one's going to be. This is also one of the lines we saw in the hydrogen emission spectrum lab. The 3 to 2 was a red line, the 4 to 2 was kind of greenish and stuff like that. Here's a question that's not hard, but it does take a lot of steps. And the question says, calculate the wavelength in nanometers associated with an energy change of 182.3 kilojoules per mole. Now, in this problem, you have a energy. It's in kilojoules per mole. And you've got to go all the way back to wavelength in nanometers. So you're going to use Avogadro's number, Planck's constant, speed of light, joules to kilojoules, and meters to nanometers in this problem. So see if you can use all this information to calculate which of those is the best answer. I encourage you to pause it. When you're ready, unpause it. We'll talk about the answer. Pause your video now. I'm going to assume that you have tried this problem and you're ready to see how you did. So without further ado, let's check it out. There's lots of equations in here, but here's kind of the idea. Energy equals hc over lambda, all right? And we're after the lambda, the wavelength. But the energy that comes out is usually joules per photon. So what we have to do here is we're going to take kilojoules per mole and turn it into an energy in joules per photon. And when we do that, we're going to get out a wavelength, but it's a wavelength in meters. And from there, we have to turn wavelength in meters into a wavelength in nanometers. So lots of different steps here. And it's all stuff you can do, but it's no problem. So what I would do here first is turn kilojoules per mole into joules per mole by multiplying by 1,000 joules per mole. And I would then take the Avogadro's number, I would divide by Avogadro's number to get the joules per photon. And that's what this number is right here, the 3.027 times 10 to the minus 19th. That is the joules per photon, the energy of the transition. But we're not done yet. We have to still convert that over into wavelength. So wavelength equals hc over the energy. And the number that comes out is this 10 to the minus 7th, answer B. And that's the wavelength in meters. But the wavelength in nanometers, we then have to divide by 10 to the minus 9th in order to get the wavelength in nanometers, 656.3 nanometers. Go through the math, make sure you can do all this. If you do have questions on any of this, be sure to reach out to me. I'm happy to help. If you divide by a power of 10, sometimes it can get tricky if you're not using the EE button. So definitely let me know if you're not getting any of these answers. This question states, what is the observed wavelength for an electron traveling at a speed of 1.20 times 10 to the 8th meters per second? Now, first of all, this is about wavelength, but this isn't like the wavelengths we've been talking about. The wavelengths we've been used previously are for electromagnetic radiation. So E equals h nu equals hc over lambda. Those are for electromagnetic radiation. If you have a particle, and a particle with mass, so for example the electron, all right, or protons or baseballs or whatever, you don't use those wavelength equations. What you want to use here is the de Broglie wave equation. So it's a different piece, and like the hint says there, when you use de Broglie's wave equation, you've got to make sure that your grams are in kilograms. So I'm going to erase my little underline there to make sure you've got it. So this would be a good place to stop it. See if you can figure out what the answer is going to be. We'll talk about the answer when you're ready, so stop the video now. Okay, I'm assuming that you've tried this problem and you're ready to check out your answers. So without further ado, let's do it. De Broglie's wave equation, wavelength equals h over mv. H is Planck's constant, 6.626 times 10 to the minus 34. M is the mass in kilograms, and v here is the velocity, the speed. That's the 1.20 times 10 to the 8th button. So if you've done all that, you got to turn the grams into kilograms. So you're going to have 9.109 times 10 to the minus 31 kilograms. But you can see here, here's Planck's constant. Here's the speed mass in kilograms. Here's the velocity. I did turn the wavelength in meters into a wavelength in nanometers. So initially, if you were looking for a 6.06 times 10 to the minus 12, none of those are out there. But however, if you turn the meters into nanometers, which a lot of times people will do, 6.06 times 10 to the minus 3rd nanometers. Femtometers, and FM, answer B, is another metric prefix. A femto is 10 to the minus 15th. It's a very, very, very small unit of length that we haven't used it, so you can probably imagine that's not going to be the right one. But anyway, sometimes just be aware the nanometers are different. Here's a set of quantum numbers, and I'd like you to tell me which of the following is not a valid set of quantum numbers. So use the rules for quantum numbers, see if you can figure out which one it is. This would be a good place to pause the video and work on it, and when you're ready, you can unpause it. Pause your video now. I'm assuming you've tried the video and you're ready to check this problem out. Let's do it. Let's review here fast about the quantum numbers. N, the principal quantum number, starts at 1, goes up in whole numbers like that. It's never negative, never 0, blah, blah, blah. L has an n dependence. L always starts at 0 and it goes up to n minus 1. So for example, on the first one there where n equals 4, L values will go from 0 up to n minus 1, from 0 up to 3. So L values here will be 0, 1, 2, and 3. There's going to be 4 possible L values. M sub L has an L dependence, just like L has an N dependence. And M sub L goes from negative L to 0 to plus L. So m sub L has to be between negative L and plus L. So if you look at A, n equals 4, that's a legit n number. L can't be bigger than n minus 1. So L of 1 is certainly less than than 3, so that's okay. M sub L depends on L. M sub L has to be somewhere then between negative L and positive L, negative 1 and positive 1. That would be negative 1, 0, and plus 1, and negative 1 is cool. A is okay. B, the second one, n equals 6 is a whole number, no problem. L is less than less than or equal to n minus 1, so 6 minus 1 is 5, that's okay. M sub L has to be between negative L and positive L, and 0 is between negative 5 and positive 5, and M sub L again of 0 is a legit number. It doesn't mean it's not there or something. B is okay too. On C, n equals 2 is legit, has to be 1, 2, 3, 4, whole number, no problem. But L of 2. Now L can be no bigger than n minus 1. So if n is 2, L has to be 0 or 1. L of 2 is not going to fly. So the problem is C here. L can't be bigger than n minus 1. Now M sub L is okay on C. If you look at D and E, all of those are okay too. But the problem here is that L can't be bigger than n minus 1. So on this problem, C is the difficult problem, the one with the problem in it. For a certain orbital, n equals 3, L equals 1, M sub L equals negative 1. And it says, what type of orbital is this? This isn't a question about the NL notation we talked about in Chapter 6, Part 1. See if you can use that information to find the right answer. This would be a good place to pause it. The video, we'll work on it when you're ready by unpausing it. Pause the video now. Okay, I'm assuming you've worked on this question and you're good to go. In the NL notation, the n number literally is 3. So because n equals 3, 3D, 3P, and 3S, sorry, I said that out of order, but those would all be legit. You wouldn't have 4D or 1F because n of 4 would be 4D, n of 1 would be that one, okay? So the answer is going to be one of the other ones. And to figure out the letter, we use the SPDF system, and those represent values of L. So 0, 1, 2, 3. L of 1 would be a P, so we would say that this is a 3P system, all right? It's a 3P orbital. If it was 3S, we would have n equals 3, L equals 0. If it was 3D, you would have n equals 3, L equals 2. But because n equals 3, L equals 1, it's 3P. This question says that if an electron subshell has 7 orbitals, what's the L value for the subshell? All right. I like to think about subshells as like houses and orbitals are like rooms. So it's saying we have some kind of a house with 7 rooms, and what's the value of this house? All right. I don't know if that works for you, but it does work for me. Anyway, this question says 7 orbitals. And remember, orbitals are the allowed m sub L values. So if you have 7 allowed m sub L values, what must the L value be? Work on this question, pause the video, and when you're ready, you can unpause it. We'll talk about the answer. Pause the video now. I'm going to assume you've worked on this and you want to answer it. Let's check this out. For this kind of problem, it basically has to do with number of orbitals. And if you have the number of orbitals, then the number of orbitals will equal 2L plus 1 if you know the L value. So number of orbitals, if you know the L value, equals 2L plus 1. So one way to do this, it's claiming we have 7 orbitals. 7 equals 2L plus 1. So 7 minus 1, 6. 6 divided by 2, this is going to be 3. L is going to be 3, okay? And that's one way to do this problem. Now, another way to do it is that 7 orbitals would mean 14 electrons, all right? And 14 electrons are what we observe in the F block on the periodic table. That would be another way and stuff to do this one. But regardless of how you do it, it should be L equals 3. Good to go. What type of orbital has two nodal planes? Now, a nodal plane is when you have a type of a plane, a place of no electron density inside the system. This is talking about planar nodes, by the way, too. A nodal plane is the same as a planar node. See if you can figure out which of those is the right answer. Pause the video. We'll talk about the actual answer when you're done and you unpause it. Pause your video now. Assuming you've already worked on this problem, let's talk about what the answer is going to be. Number of planar nodes equals L. All right, number of planar nodes equals L. And so in this case, there are two planar nodes. So that means that L is going to be 2. So going back to our SPDF kind of thing, the L value 0, 1, 2, 3. When L equals 2, you're going to have a D subshell. This is going to be D. All right, it's a D orbital is going to have two planar nodes. So planar nodes equals L. If you have two planar nodes, that means L equals 2, and L equals 2 is a D subshell. Spherical nodes are N minus L minus 1, but this one is about nodal planes or planar nodes, so it's just the L value which is important. Which of the following orbitals has two spherical nodes? And there's 5 possibilities here. Remember from the last one, number of spherical nodes equals N minus L minus 1. So see if you can figure out from this list what that answer is going to be, and we'll talk about it in a minute. So pause the video now, and when you're ready, you can unpause it. We'll check it out. Pause your video now. I'm assuming you've tried it and you want to look at the answer now. So without further ado, let's get into it. So number of spherical nodes equals N minus L minus 1. And you want to have N minus L minus 1 equal to 2. All right. So we're trying to find here an example of where that's the case. So 1s would have n of 1, and remembering SPDF stands for L of 0, 1, 2, and 3. 1s would have L equals 0, so 1 minus 0 minus 1 would be 0, so it's not the first one. That's not going to fly. For B, n equals 2, P means L equals 1. So for that one, you would go n of 2 minus 1 minus 1. That's also 0. That's not going to fly. The next one, n equals 3 for 3D. D means L equals 2. So we go 3 minus 2 minus 1. That one also has 0. That one's not going to do anything. D, 3P, n equals P, 3 equals means L equals 1. So we would go 3 minus 1 minus 1, 1 spherical node, but it doesn't have 2 spherical nodes, so that's not right. So let's open the last one. 4P means n equals 4, P means L equals 1. 4 minus 1 minus 1, that one's going to have 2 spherical nodes. So answer E would be the best way. And notice again how I use the N and L values to find the number of spherical nodes, knowing that SPDF number system obviously is kind of important for this stuff. Cool. Chlorine has an electron configuration, one of the answers shown below, and see if you can figure out by hook or by crook which one of those it is. What we'll do is pause the video now, work on it, and when you're ready you can unpause the video. We'll talk about the answer. Pause the video now. I'm assuming that you've worked on the problem and you want to see how you did, so without further ado, let's go ahead. Chlorine on the periodic table is number 17. It's Cl, all right? And 17 means that in neutral chlorine, you would also have 17 electrons. Now, one way to do these kind of problems is literally just to add the superscripts together and see if they equal 17. So for example, on the one I just did, 1s2, 2s2, 2p5, that would be 2 plus 2 plus 5, 9. 9 is not 17. C is not chlorine. C is actually fluorine when you figure it out. Same thing for the next one, D. If you count up those electrons, there's 18, and 18 is obviously not 17. D could be, for example, argon. Xenon has, I believe, 54 electrons, so that's way, way too much. The last ones and stuff, if you look at them carefully, only the B has the right number of electrons, all right? It has 2 plus 2 plus 6, that's 10, plus 2 plus 5, that would be 17. The top one has 2 plus 2 plus 6, 10 plus 5, that would be 15. Also, 3s can't have more than that, so that one's out. The answer here is going to be B. Make sure that you follow electron filling orders, 1s2, 2s2, 2p6, 3s2, and then the remaining 5 electrons go into the 3p. Answer B would be correct. What element has the electron configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2? Now, only thing tricky about this problem is that this is an example of an electron configuration based on making an ion. And if you're actually filling the electrons in, the 4s would be filled in before 3d. But you will see these listed sometimes this way, and that's why I'm throwing it in. But anyway, see if you can figure out which element it is. Pause this video, and when you're ready, unpause it. We'll talk about the answer. Pause this video now. I'm assuming that you've worked on the problem and you want to figure it out. So again, a couple different ways to figure this out. If you count up all those superscripts, that comes out to be 30, and 30 is, of course, zinc. On the other hand, what you could do, you have a filled 4s2 set, and you have a filled 3d10 set. So the 3d block goes from scantium, number 21, over to zinc, number 30, and because it is a filled 3d10, D's hold up to 10, that's going to be zinc as well. So for all of these reasons, it's going to be zinc. All right. You can also probably see why chemists like the noble gas notation. You could also call this argon 4s2 3d10, but that's okay. Again, the 3d10 4s2 you will see sometimes because when you take electrons away from zinc, the 4s electrons come out first before 3d. But either way, you're smart enough, you'll figure this out. The electron configuration for tin is, and there's 5 possible answers. Now, tin is Sn on the periodic table. It's number 50. So see if you can use that information to figure out what's going on here, and pause the video, unpause it when you're ready to talk about it. Pause the video now. I'm going to assume that you've worked on this problem and you're ready to look at it and stuff, so let's check it out. Okay, so tin, number 50, is in the P block, all right? And knowing where tin is on the P block can be really helpful. So example of that, boron is a 2p. It's in the second period and the P block. Aluminum, right below it, is the beginning of the 3p block. Likewise, gallium, Ga, would be the beginning of the 4p, and indium, number 49, which is right next to tin, indium would be an example of something in the in the fifth period, 5p, okay? So the outer electrons here for tin are not going to be 4p's, they're going to be 5p's. And you can probably imagine that 50 electrons is certainly a lot less than 118 electrons, so that one is flat out too. So anyway, I'm digressing, my own silly joke sometimes it made me distracted. Anyway, 5p. So 5p1 would be indium, and that means that tin would be 5p2. But you can see the difference between the answers C and D is, do we use krypton or do we use xenon? And it kind of feels like maybe you should use xenon because it's a lot closer to tin than krypton is. But the rule is you always go backwards. Krypton has 36 electrons to it. So if you added 36 to the superscripts that are left, 36 plus 2 of 5s plus 10 for 4d and 2 for 5p, you're going to get 50. Xenon, on the other hand, is 54. That's more than then tin's 50 electrons, so it can't be that one. So the answer here is going to be C, all right? And notice there how I used my knowledge of the blocks and the numbers to figure out, you know, what would be the P block. Tin is definitely a 5P system, and if indium was 5P1, then tin would be 5P2. And finally, you have to go backwards for noble gases. You can't go forwards. So it's not going to be xenon. Xenon would have more electrons and stuff than that. It's going to be the krypton. Cool. What element has the following electron configuration? And you can see it has a neon core, a 3s2, 3p4. See if you can use this information to see which of those answers is correct. I recommend pausing the video, working on it. When you're ready, you can unpause it. Pause the video now. I'm assuming you've worked on it. You want to see how you did, which is fantastic. One way to do this is just to add electrons. So neon is 10 on the periodic table. That means 10 electrons, plus 2 for 3s, 12, plus 4 for p's. That's 16 electrons total. So probably here the answer is going to be B, sulfur, because sulfur is number 16 on the periodic table. But you could also find the raw configuration of sulfur. Sulfur is 1s2, 2s2, 2p6, which would get us to the neon core in brackets there. 3s, 3p4. Whatever reason, this answer here is going to be sulfur. Cool. So you can count electrons, you can see where they are in the periodic table, whichever way you want to do to figure out how this stuff all works out. What element has the electron configuration xenon, 4f14, 5d10, 6s2, 6p2? Now notice again, like on a previous example, this is written in a slightly different way. This way is used for taking electrons out of neutral atoms if you're making ions. If you were to fill this in, 6s2 would be the first ones to be filled in, then 4f14, then 5d10, etc., etc. But use your knowledge of the periodic table and electron configurations to make your prediction as to which of those elements would be the best answer. So pause your video, and when you're ready, you can unpause it. We'll talk about the answer. Pause your video now. Okay, I'm assuming you've worked on the question. You want to check out your answer, which is fantastic. In the earlier question, we went down the P blocks to figure out where tin was. And for example, I saw that boron B was the beginning of the 2p block. Aluminum was 3p, gallium was 4p. Those numbers do come straight from the period number. So periods go left to right. Hydrogen and helium are 1, lithium through neon are 2, etc., etc. And I state that because the outer electrons here are 6p2. So if we can see where the 6p starts and then go like 2 electrons over, we're good to go. 6p1 begins at thallium, number 81 on the periodic table. If that's the 6th period, p blocks, you use that number directly. So thallium would have all of that, but with only a 6p1. And right next to it is lead. Lead would have a 6p2 configuration. So this is an example of a way to find it. All the filled orbitals, we don't really care about that much. We're kind of after the last ones. That will help us figure out what element it is. It's always the outer electrons which help define which element it is on the periodic table. This is a question about electron configuration of ions, specifically an anion. And I'd like you to tell me what's the electron configuration of phosphide, P-3. So this would be a good chance to pause the video, work on it a little bit, unpause it when you're ready to talk about it, see how you did. Pause the video now. I'm assuming you've worked on it and you want to check this question out. When I do these kind of problems, I start with the neutral version of the atom, which in this case would be phosphorus. And phosphorus, neutral phosphorus, is actually listed in this problem. It's answer B. Neutral phosphorus is a neon core, 3s2, 3p3. It's got 15 electrons. It's 3 into the p block and stuff, so phosphorus is 3p3. But here we have phosphide, so we have to add 3 more electrons to neutral phosphorus to make phosphide. And those extra electrons just go in the lowest empty spots. Like we've talked about, the p blocks can hold up to 6 electrons, so those extra 3 electrons can just go in the 3p area. Phosphide is going to be a neon core 3s2 3p6, the same as neutral phosphorus, but with 3 extra electrons filling it in, same electron configuration as argon. Most of the main group metals and nonmetals will adopt a noble gas electron configuration. So of those 4 possibilities up there, only E neon and A neon 3s2 3p6, which is argon, would be noble gases. Those would be the best places to start, but we figured out, because we're cool, that A is the best answer. All right. In this question, it says, which ion corresponds to the following electron configuration? And notice here what's going on. We got argon, we have 3D, and there's 2, 4, 5, 6, 7. That's a 3D7, and a 4s, which is empty. So this is going to be a positive ion, because transition metals lose 4s electrons first before losing any 3Ds, if they're in the 4th period. If there are other ones, then they might lose 5s first or 6s. So see if you can use that information to see which of those ions corresponds to this configuration. This would be a good place to pause the video, unpause it when you're ready to talk about the problem. Pause the video now. I'm assuming you've worked on it and you want to see how you did, so let's check this out. Now, what I would do in this problem is this thing has 3d7. So that's 2 electrons, 4 electrons, 5, 6, 7. Hund's rule says put them all in their own box first, only pair them up when you have to. But the important part is 3d7. So what I would do is I'd try and find what the neutral version of this atom is. And a neutral version would just have a 4s2 filled up. So on my periodic table in front of me, I'm going to start with scantium, Sc, which would be a 3d1. And I'm just going to move right until I get to 3d7. So scandium 3d1, titanium next to it would be 3d2, vanadium 3d3, chromium 3d4, at least in theory, it's one of the freaks of the n plus L rule, but I digress. Manganese 3d5, iron 3d6, and lo and behold, cobalt would be 3d7. So if we had neutral cobalt, we would have an argon 4s2, those are always filled in first, 3d7. But this thing has an empty 4s orbital, so it's least going to be a positive 2 charge. So it makes kind of sense that with cobalt plus 2, you'd pull those 4s electrons off and you'd have 3d7 left over. And that's exactly what it is. So this answer is going to be the cobalt plus 2 ion. All right, if you figure out the charges of the other ones, the iron plus 3 would be argon 3d5. The nickel 2 plus would be argon 3d8. The rhodium would have 4d electrons. It's in the next group down. So rhodium would have a 3d10 as well as a filled 4s2 and 4p6 for that matter. That one doesn't count. And lithium plus 1 would be just a 1s2. Lithium doesn't have that many electrons, so that one wouldn't be a good choice here. The answer here is definitely going to be C. Which of the following ions is diamagnetic? And there's 4 possibilities here. Now, diamagnetic ions have just as many ups electrons as down electrons. Paramagnetic ions have at least 1 electron that's up without a down or down without an up. Use this information to see which one, if any of them, are diamagnetic. This is a good place to pause your video. I'll talk about it once you unpause the video, how to answer it. Pause your video now. Okay, I'm assuming that you've worked on this problem and you want to see how you did, so let's check it out. Of all of the ions up there, all right, a lot of them, at least titanium, vanadium, and chromium, have d electrons, all right, and d electrons are spread out through 5d orbitals. So to be perfectly honest, the chances of a transition metal being diamagnetic are not very good. Zinc 2 plus would be an example of a diamagnetic ion. But the other ones, because you lose the 4s electrons first, almost always the transition metals will be paramagnetic. So knowing that, let's talk about magnesium 2+. Now magnesium has a neon core with a 3s2 on top of it. And if you take away 2 electrons from that, those are going to be the 3s electrons. Magnesium 2+ is going to have a neon core. And guess what? All of the noble gases are diamagnetic. So if you have to guess as to which one is a diamagnetic ion, it probably won't be the transition metal lanthanide or actinide. It's not impossible, but it's very, very rare. It's more likely to be a main group metal or non-metal that has lost or gained enough electrons to be like a noble gas. And in this case, that's definitely going to be the magnesium ion. Which of the following is the correct electronic configuration for the nickel 2 ion? All right, so nickel is number 28 on the periodic table, and I'd like you basically to give me the electron configuration for the nickel +2 ion. So use your information of this to work on this. This is a good place to pause the video. When you unpause it, I'll talk about the answer. Pause the video now. I'm assuming you've worked on it. Let's see if we can figure out how you did on this one. So when it comes to ions, I usually try and start with the neutral atom first, and then I work my way to whatever the ionic charge is. And nickel, like we said, was number 28. So nickel has an argon core, which I'll try to write right here. And then the next 2 electrons, potassium and calcium, make it a 4s2. And then you start the d electrons. Nickel, if you count from left to right, is a 3d8. So neutral nickel would be argon 4s2 3d8. That would be neutral nickel, okay? But we don't want neutral nickel, we want nickel 2+. Nickel Roman numeral 2 means nickel 2+, and +2 means that you've lost 2 electrons. So the question is, where do the electrons come from? And the official rules are you always take them from highest n first, and if there's a hot tie, then you go to highest n plus L. But here there is certainly no tie. 4 of 4s is n equals 4. And that's bigger than n equals 3 of 3d8. So in this case, the 2 electrons to be lost are the 4s2 electrons. So what's left then with the nickel 2+ would be argon 3d8. That would be the electron configuration for this ion. Remember, this is really important with transition metals. Highest n comes out first. That usually means the s2 electrons in front, and then the d's, whichever one you're looking at, would be left after that. Tin 2+ is another possible ion you can do. We talked about neutral tin earlier. See if you can use your information and knowledge of these to find what the correct electron configuration of tin 2+ would be. And again, this is a good place to pause the video. When you're ready, unpause it. We'll talk about the answer. Pause the video now. I'm assuming you've worked on it. You want to see how you did. So without further ado, let's check this out. All right, we talked about tin earlier. All right, it's a krypton core. All right, krypton is the most recent noble gas. And then after that, we have 5s2, 4d10, 5p2. Okay, so krypton, 5s2, 4d10, 5p2 is the configuration for neutral tin. And again, these configurations are all written a little differently, which you'll see sometimes, but that's what the first one is right there. That would be neutral tin. But we don't want neutral tin. We want tin +2. We want neutral tin without 2 electrons. So the question here comes, where do the electrons come from? We've got 5s, 4d, and 5p. So again, back to the rules, highest n first, which means we're going to take it from either 5s or 5p, but not 4d, because 4 means n equals 4, 5s and 5p both mean n equals 5. So if you have a tie, like this one, 5s and 5p, you take it from highest n plus L. 5p, p as L equals 1, and 5s, s is L equals 0. So we're going to take them from the 5p before we take them from 5s. Another way to think about it is if you get to the tie, then it literally is last electrons in are first electrons out. 5p electrons were the last ones in. So for all of those reasons, we're going to take the electrons from 5p2. The actual configuration will be B. Krypton 5s2 4d10. So again, on this problem, we knew we had to take away 2 electrons. We didn't know which ones. N equals 5 will come out before N equals 4. And then the 2 electrons will come from 5p first, highest N plus L before 5s. Now, if you're going to make a 10 plus 4 ion, you would take the next 2 electrons from 5s2, because again, N equals 5 comes out before N equals 4. So you can kind of see how this works out. The d electrons are sometimes usually the last ones to come out, or at least it takes more energy to get them out. That would be a better way chemically to think about it. Let's compare these 4 elements with regard to some of the periodic properties. And the question is, which one has the largest atomic radius, i.e. which one has the largest size, which one is biggest? Use your knowledge, work on it. This is a good place to pause if you'd like to, and then when you're ready, unpause it. We'll talk about the answer. Pause your video now. I'm assuming you've worked on it. Let's see how you did. When it comes to size, left and down on the periodic table makes for bigger atoms. So using a periodic table of those 4 elements, look for the one which is more left and down on the periodic table. Carbon is most up and to the right of all of those. And then you can see that boron and aluminum would be next. Boron is more left, aluminum is more left and down, but by far sodium is most to the left and down. So we would argue, just based on the position of the periodic table, sodium is the biggest atom. So again, left and down for atomic size. Left and down also works for ionic size, as long as you compare cations to cations or anions to anions. Cool. This question is basically about the sizes of anions or sizes of cations. And as long as you're using the same kind, anions or cations, you can do this. These are all basically anions. So it says which of the following is expected to have the largest radius? And you don't need to use a table. I'll let you know that right now. See if you can figure out what it is. If you want to pause it, we'll then talk about it when you unpause it. Pause the video now. I'm assuming you've worked on it. You want to check your answer out. Let's get into it. When it comes to ions, it's the same thing as sizes for when it comes to periodic trends, left and down. Now, when it comes to ions, as I said, you can only compare anions to anions, like we're doing here, or cations to cations. You can't compare anions to cations. Anions are always bigger than cations, so it doesn't work. But in this problem, it's okay. You just want the atom which is most left and down. And if you look, argon, chlorine, sulfur, and phosphorus are all there on the 3rd period of the periodic table. And the one that's most left and down, phosphide. All right. Phosphorus has the most electrons and the fewest number of protons, so the electrons tend to wander a little bit more. That's why phosphide here would have the largest radius. So again, as long as you're comparing ion sizes and it's the same kinds of ions, left and down for the largest one. Let's compare those 4 elements we talked about in a previous problem once again, but which one has the largest electron affinity? Now, electron affinity is usually mentioned as most negative, i.e. most exothermic. You don't worry about that. You let me just ask the questions, and I'm going to be consistent on these. Which one has the largest electron affinity? So use your knowledge of electron affinity to figure out which one of those is the biggest. Pause your video now. When you unpause it, we'll talk about it. Pause your video now. I'm assuming you've talked about it. Let's get into the answer. Electron affinity periodic trends go up and to the right. So up and to the right means the largest, which means the most negative in weird electron affinity culture. So we want the atom most up and to the right. And earlier we saw that sodium was most to the left and down, so that wouldn't be the best answer. Aluminum and boron would follow, but carbon is most up and to the right. So we would predict that carbon has the highest electron affinity. And again, electron affinity's periodic trends are not by any means perfect, but if you have to guess and you don't want to look up Google, or you can't look up Google for information, this would be the next best thing to do. Up and to the right for ionization energy and electron affinity. Speaking of ionization energy, this question says, which of the following groups of elements is arranged correctly for order of increasing first ionization energy? And as we talked about earlier, the trend you want to follow is up and to the right on the periodic table. So see if you can figure that out based on this information. If you want to pause the video, then you can unpause it when you want to talk about the answer. Pause your video now. I'm assuming you've already worked on the question. You want to see how you did, so let's get into it. Ionization energy's periodic trends increases up and to the right. So you look for periodic table elements, and you want to go up and to the right. Magnesium is definitely most down and to the left. So magnesium should have the smallest first ionization energy. And then up and to the right, if you watch the periodic table, carbon would be first as you go left to right. Nitrogen would be next. Fluorine would be the ultimate one. So in this one, answer A would be the best answer. And again, we started in the lower left and went to the highest upper right, if you will. Magnesium, carbon, nitrogen, fluorine. And I promise I won't ask you questions, for example, like boron versus silicon. Boron is more up and to the left, but silicon is more down and to the right. I won't ask you those kind of things. I think of that as kind of dirty poker. We're just going to do basic kind of things to get through these periodic trends. That's the end of this review. I hope this was a useful time to you. If you did get stuck on any of them, any of the questions, definitely email me and I can totally help. There are more ways to practice the problems. There's practice problem sets, which you can do online or from the companion. Concept guides are available, which have worked questions followed by the answers. Chapter guides have kind of an overview of what's happening. At the end of every lecture that we did on the different chapters, there are some end of chapter problems, questions followed by the answer. You can check yourself. I totally know you can do this. Again, if I can help in any way, you let me know. Good luck with your studying and have a wonderful day.